This is Dr. Tanveer Ahmed and I welcome you to the course of Financial Econometrics. This is our lecture 9 and we are going to discuss regression assumptions in this lecture. So let's move toward the contents. So previously we have developed our understanding of a regression model and we have seen that there are parameters that we can find out using certain formulas, and then we have understood what OLS is, which stands for ordinary least square. We did an exercise on ordinary least square, and now in this lecture we are going to develop our understanding that to use the OLS model or to use the OLS technique, there are certain assumptions that we need to fulfill. So we are going to introduce those assumptions, and then we have a specific whole chapter on each of that assumption. So we are going to have a introductory to a medium kind of approach towards these assumptions in this lecture, and then when we will be discussing each of the assumptions individually, then we would have a deeper look into it. So we are going to discuss each assumption. So let's move forward. Now the objective of regression was, we have seen, was not just to find or obtain the estimates. We saw that the objective was to obtain estimates and as well as draw an inference based on those estimates. So we used OLS technique to find the parameters, the betas, and then we need to draw some inference from those betas. But to draw a valid interpretation or inference from the estimates that we have obtained from OLS technique, there are certain assumptions that the technique makes about the way the independent and the error term, and we need to look at those assumptions, and those assumptions need to be fulfilled before we can reliably interpret the parameters obtained using the OLS technique. So these basically are the classical linear regression model assumptions. And let's see what are those assumptions. The first one is the linear regression model. The model should be linear. The error term should be normally distributed. Then there is an assumption of homoscedasticity. The error should the error term should be constantly the distribution of the error term should be constant. The variance should be constant. Then there is an assumption of no autocorrelation. There shouldn't be any autocorrelation between the error terms. Then we have the assumption that the number of observations should be greater than number of parameters and non-constant assumption of X. Then we have no multicollinearity assumption and the exogeneity assumption. Now, in some cases, in some books, you would find that there are 7 assumptions. Some would refer to 10 assumptions. But you need to understand that some of these assumptions are clubbed together in a group. So it doesn't matter the number of assumptions. These are basically the main assumptions that we need to look into. Some of them take these assumptions such as n should be greater than the number of parameters and non-constant x as being obvious, and they do not report them explicitly. But anyhow, these are the assumptions, and the numbers wouldn't matter, but we need to fulfill these assumptions before we can apply the OLS technique. So let's start with the first one, the linear regression model. And before I move forward, what basically these assumptions would do is that they would either affect the coefficient or the standard error. And by means affecting, I mean that they would, if these assumptions are not fulfilled, they wouldn't be reliable. So these assumptions make the coefficient and the standard errors reliable. And just for the sake of simplicity, The standard error is basically the standard deviation of the coefficient. So it's basically standard deviation of a sampling distribution, but for the sake of simplicity, let's just say that standard error is just a standard deviation of the coefficient. So let's start with the first one, the linear regression model. So the first assumption that we are going to understand is the linear regression model. The model should be linear, and it is also called the assumption of linearity. Simply put, the relationship between this assumption states that the relationship between the independent variable and the dependent variable should be linear. It should be represented by a straight line. But before moving to understand what linearity can be further divided into two subparts, linearity in variable or linearity in parameters. So we know that this x is a variable and this beta 1 alpha is the parameters of this model. So linearity in variable means that the variable would be linear. So in this case, this model where we have a quadratic term is not linear in the sense that there is no linearity in variables, right? But although the parameters are linear, this specific equation we have this x term which is linear, so the variable are linear. In case of this linearity in parameters, we can see that we have this term which is beta square. Obviously this is not linear in parameters. So the linear regression assumption states that the model should be linear in parameters. It can or cannot be linear in variables, but it should be linear in parameters. And this would be better understandable with this table. We have this model linear in parameters and model linear in variables. So a model linear in parameters and a model linear in variables. So a model that is linear both in parameters and in variable would be called a linear regression model. But also, if a model is linear in parameters but not linear in variables, again that would be considered a linear regression model. But being linear in variable or not wouldn't matter if that specific regression model is not linear in parameters. So in that case, it would be a non-linear regression model. So what this assumption states that the model should be linear in parameters. So this is what we just stated, that the regression model should be linear in parameters. It may or may not be linear in variables. So in this case, this example where we have dependent variable and independent variable, in this case, this independent variable is linear in and this parameter is also linear. So this specific equation is linear. So this fulfills the assumption of a linear regression. But even if there was a quadratic term or log of x or any other transformation being performed on this variable, even then this specific equation would be linear and this linearity assumption would have been fulfilled. Now, one thing that I would like to restate, I have previously discussed, but sometimes I would use this beta 1 or beta naught or alpha. They all represent the same parameter which is constant, right? So there are different notations that are used, but they all would represent constant. Let's move towards our second assumption, which is the assumption of normality of error term, or also called the zero mean value of disturbance. Disturbance is the error term or the residual. They all represent the same term. So we can either call it disturbance term, error term, or residual. So what this assumption states is that given the value of x, the mean or expected value of the random disturbance term should be 0. And symbolically it can be represented as expected value of the error term given or conditional upon the x value should be 0, or the expected value of the error term should be 0. Sometimes this assumption is referred to as zero mean value of disturbance. In some books you would find it as normality of error term. They both are similar, and in the coming slide I would explain how it doesn't matter whether you call it a zero mean value or normality of error term. They both would work. So from this graph we can understand, let's first understand what is normality, and we have already discussed it multiple times. Normality is when we have a data that can be placed on in a bell curve shape. So let's say if we take the data of heights, we have heights and we have number of individuals, so we have frequency and we have the data of heights. So we know that majority of population, the frequency is on y-axis and height is on x-axis. So we know majority of the population would have a height of mean, around mean, say 5 feet or 5.5 feet, and some would have higher, would be taller, and some would have a quite short height. So the point is that the data is normally distributed around mean, equally distributed around mean, and the mean and standard deviation alone can define this data. So similarly, if we these dots are error terms, these are the actual observations, and this is our estimated value of so if we look at the difference between the estimated value and the actual observation, we would call it error term. Now for any given x, these error terms should be normally distributed, and when they are normally distributed, some of them would be below the regression line, some of them would be above the regression line, some of them would be positive, others would be negative. So in essence they would cancel each other out, and the expected value of the error term would be 0. So what this normality of error term assumption states that for any given value of x, the error term should be normally distributed and they should have a mean value of 0. So the only thing that would be changing in this case is that the change in the mean value of y, which is increasing as the x is increasing. So the intuition behind this assumption is that we know that what is error term? It is the term that includes the residual effect, the effect of all the components or variables that we haven't included in the model. So all the factors that aren't included in the model, their effect would be summed in the error term. So what this assumption simply says is that the factors that are not explicitly included in the model, that are there in the error term, they would not have any systematic effect on the value of y because they would be cancelling each other out. So moving on to our next assumption, which is homoscedasticity, also called the constant variance assumption. Let's divide this term and we would be better able to understand it then. Scedasticity basically means the variance or the dispersion. So what this homoscedasticity says is that the variance of the error term should be equally distributed, and that's why we call it a constant variance assumption, because we want the error term to have a constant or same variance. And when this assumption is violated, that situation would be called heteroscedasticity. In that case, the variance term, the dispersion would be different for the different error term at different x values. So the variance of the error term or the disturbance term is the same regardless of the values of x. So for each x value, so this is called the conditional variance should be same, and this would be represented as variance should be equal to sigma square, or variance of y given x conditional variance should be equal to sigma square. And when that is violated, that would be heteroscedasticity, and it would be represented as this, where we would have a different sigma value or variance value for different value of x. So graphically, if we represent this, then we have different x value, and this we have probability density of the error term. We have this regression line, and these are the distribution of error term. Now we can see that the dispersion between these error terms is constant no matter what the x value is. So for all the values of x, the variance is constant. Remember how we can see the variance. So in this case, this graph would have a lesser variance as compared to this one. So this would have greater dispersion and hence greater variance. So if the graphs were different, the curves were different for different values of x, so they were increasing or decreasing in a systematic way, then we would say that the constant variance assumption is violated, and we cannot fulfill the homoscedasticity assumption, and we have the problem of heteroscedasticity. So when this assumption is violated, we have a problem of heteroscedasticity, and this graph would better depict the idea. We can see that in case of x1, the disturbance term have a lower variance, and the variance increases as the value of x increases. So if this was our let's discuss an example of income and expenditure. So if we are studying the effect of income on expenditure is our dependent variable and income is our independent variable. Then from this graph, we would see that the higher the income, the higher the expenditure. This is what this graph represents, the previous graph. But in higher income, the expenditure can be higher or lower. That means the dispersion is higher. The standard deviation is higher in higher income level, whereas in low income, the expenditure will be lower because they do not have the choice. So let's move back towards the graph. So let's say on this x-axis we have income, and on this y-axis we have expenditure. Then this would mean that as income increases, expenditure increases. That is understandable. But by the shape of this curve, we can interpret it that the expenditure have more dispersion, more variability in for the richer people, and lower variability for the lower income segment. So that means in this specific income group, we have a lower variance. The standard error would be lower. This data is more reliable, whereas this data would be less reliable. So you can get an intuition of this assumption. We would want to have a constant variance for all the values of x. So if this homoscedasticity assumption is violated, mainly the standard error would become unreliable, and we know that the t values or the p value is calculated by dividing the coefficient divide the coefficient by standard error. It's not D, it's E, standard error, right? So if the standard error would increase, the t value would decrease, but in any ways there would be more chances to get insignificant relationship, and these standard errors wouldn't be reliable.